Welcome back. Week 2, Module 2, we're talking about georeferencing. Last time I kind of introduced georeferencing and why you need to do it. If you're going to assign a location to your data, you need to do what's called georeferencing. And in order to do georeferencing, you need to specify some things so that other folks who are going to use your data with their data will be able to put it on a common reference. So that's kind of what georeferencing is all about. Remember that we're going to need help from some scientists called geodesists, and they're the ones who are really good at measuring and monitoring the size and shape of the Earth. So we think of the Earth as a sphere, but it's not. It's what's called a spheroid. So a spheroid is basically an ellipse that's been rotated about one of its axes. If you rotate it about the east-west axis, it's going to be called a prolate spheroid. If you rotate it about the north-south axis, it's going to be oblate spheroid. The Earth rotates about a north-south axis, so we're going to call the Earth an oblate spheroid. Sometimes this oblate spheroid is called an ellipsoid. Okay, ellipsoid, oblate spheroid, same diff. Common ellipsoids. There are 3 that are generally used in North America, so a lot of the data you'll see in North America is based upon one of these 3. The older data uses the Clark 1866 ellipsoid. This was developed before satellites when they didn't really know where the center of the Earth was, so what they did was they made the ellipsoid go through a certain point on the Earth that's you'll see on the last map, probably somewhere around the eastern central portion of the United States, and then everything else fit to that. So there are some large kind of errors if you use this ellipsoid in other continents or other parts of the globe. Satellites came around, and by 1983 they started using what's called the Geodetic Reference System 1980, the GRS-80 ellipsoid. This is an Earth-centered ellipsoid. It's much more accurate. It can be used around the Earth because satellites, of course, are going to need to be able to use things around the Earth. GPS system and NASA came around, and they started using what's called the WGS 1984, World Geodetic System 1984 ellipsoid. So these are 3 different ellipsoids, and looking at some of these numbers here, you can see that there are small but not insignificant differences in the shape of those ellipsoids. So if you're locating something on one ellipsoid, you're going to have a different location than if you locate it on another ellipsoid. So we pick an ellipsoid, specify a latitude and a longitude. We're going to be able to locate a point on that surface of that ellipsoid. And of course the latitude and the longitude sound kind of like coordinate system measures, and they are measures. They're not linear measures like I showed in the last video, but they're angular measures. A longitude is along the equatorial plane from the prime meridian. The latitude is from the equatorial plane up to that point. We've got to be careful where we measure this from. If you connect that point P to the center of the Earth, A, you're going to get a latitude, in this case of 60 degrees. If you just take a perpendicular up here and draw the perpendicular to the ellipsoid down to here and measure the latitude, you're going to get a different latitude. So the perpendicularly measured latitude is what's called the geodetic latitude. The one that goes to the center is called the geocentric latitude. So when you hear geodetic and geocentric, you need to think about the difference between those 2. Geodetic is generally more associated with a gravitational measurement. Geocentric is more with a mathematical measurement. So we have to worry about gravity too, because the Earth isn't a nice uniform sphere, and so gravity is going to vary around the planet. Newton was the guy that came up with this law of gravitation. There's Newton's coat of arms, and here is the Romance version of Newton. Newton's law of universal gravitation says the force between 2 objects is proportional to the masses of the object. A big mass is going to pull a small mass toward it, and it's inversely proportional to the square of the distance between the 2. So if I'm on the surface and there's a lot of mass a long ways away from me, it's not going to pull as hard as if there's a lot of mass close to me. So when you think of yourself on the surface of the Earth and draw a line between yourself and either at a perpendicular or to the center of the Earth, if you think about the fact that you're going to have different densities of material between you and the center, you're going to have different forces of gravity depending upon where you're at on the surface of the Earth. There's a set of satellites called the GRACE satellites that NASA put out that actually measured gravity around the planet. This shows gravity compared to the average gravity. So 0 is an average gravity around the planet. The blues are lower than normal gravity, and the reds are higher than normal gravity. So you can see, depending upon where you're at on the planet, you're going to have a higher or a lower amount of gravity than average. So the geoid is going to model this difference in gravity. There are a bunch of geoids. You can go out to the NGS website, and at the bottom of this you see that there are a bunch of geoids that have been defined since 1996. So if we're going to model elevation, we need a geoid, because geoid is going to model things with respect to gravity, and elevation needs to be modeled with respect to gravity. So the geoid is a model that fits mean sea level. And you can see here we have the spheroid in green. The geoid is the curve labeled number 5 here, and we have water. Where the geoid goes over water, of course, that would be mean sea level, because that is mean sea level. But where the geoid goes over land, there's a difference between the geoid and the ellipsoid depending upon where the masses are at. So when you measure elevation, you need to know what the geoid height is. If you measure from the ellipsoid, you're not going to get the same elevation as if you measure from the geoid. So what you basically generally do is you use the ellipsoid for your reference, and then knowing what the geoid height is around the planet, you're able to correct that ellipsoidal reference to get a reference that you can use to measure a gravitational elevation. Kind of complicated, but you need to do it because it makes a difference. Here's a map that shows the difference in the geoid height, the difference between the geoid and the ellipsoid around North America. If you look here in the Idaho area, you see yellow-orange. Yellow-orange is probably somewhere in the vicinity of 15 meters. So the geoid is 15 meters below the ellipsoid in Idaho. So you can see it makes a difference. 15 meters, 45 feet, that makes a difference. What is a datum? A datum is a collection of points that have been precisely located so that you can use those as your reference. So the datum has taken into account the ellipsoid and the geoid and precisely located a point, and then you can use that as your reference, knowing that it's based upon an ellipsoid and a geoid. So the ellipsoid is going to give you a horizontal datum, and the geoid is going to give you what's called a vertical datum. So an ellipsoid and a geoid combined with a coordinate system, that's a datum. Using those three things, you can precisely locate points that then you can use as a reference. So in practice, things like survey markers are a datum. You don't need to know where the center of the Earth is or what the geoid looks like. If you know where a survey marker is and what its location is, you can use that as your reference and measure from there. What datum you use makes a difference. This is a vertical datum comparison, so the two main datums are the NAVD 88 and the NGVD 29, so 29 is older than 88, and you can see that depending upon where you are in the country, you have a difference in datums. And so in Idaho again, we've got green, yellow, that's 120 centimeters difference. So if you give somebody something in NGVD 29 and they use it on NAVD 88, it's going to be off by 120 centimeters. How about horizontal datums? This is the datum shift between the old ellipsoid, the GRS, and the GRS 80. So this is the Clark ellipsoid, and this is the GRS 80 ellipsoid. And you can see that according to these contours, there's really no difference between the two there. So you can imagine that that might be the part of the Earth that the old ellipsoid intersected with. But as you got further and further from that intersection point, you can see that the newer ellipse is going to get further and further from the older ellipse. So by the time you get to Idaho, you're maybe 70 meters different between the two, 210 feet horizontally. So that's going to make a big difference if you give it in one datum and somebody else uses it in another. Okay, so datums are important. What is a datum? It's a geoid, it's an ellipsoid, and it's a coordinate system. The ellipsoid is this smooth surface. The geoid is a model of mean sea level that takes into account gravity. So if you combine the geoid, the ellipsoid, and the coordinate system, you're going to be able to measure or assign location to this data that you've got. So next time I'm going to start talking about how you get from this three-dimensional object, which is what we've been talking about, a bumpy ellipsoid basically, to a two-dimensional map. And the way you're going to do that is you're going to use a map projection. So I'll start talking about map projections next time. Thanks for viewing.